Welcome to Pomodoro Joe for Wednesday, September 27th, 2023. Today we're looking at LeetCode problem 880, decode string at index. This is a medium problem. All right, so in this one we're given a string, s, and the string is encoded. It's got some lowercase letters and some numbers. Now to decode the string, we need to decode it to a tape. So the decoded string will be much longer than the encoded string. To decode the string, we have to go through one character at a time. If the character is a letter, then that letter is written onto the tape. If the character is a digit, then the entire current tape is repeated that many times. So they say it is repeatedly written d minus 1 more times, but basically we just take the entire tape and repeat it d times. Given an integer k, return the kth letter. This is a 1 indexed in the decoded string. All right, so we have an example. Leet and then 2 and then code and then 3. So we would write L-E-E-T, then when we get to 2, we would double leet, so it'd be leet, leet. And then we'd do C-O-D-E, and then when we get to 3, it'd be leet, leet, code 3 times. So we have leet, leet, code, and leet, leet, code. Now our index is k, so we have to go to the kth index starting at 1. So let's see. So that's 4, 8, 9, 10. That's this O. All right. And let's look at our constraints. The string, the input string, the encoded string, is less than 100 characters, greater than 2 characters, and it consists of just lowercase English letters and digits 2 through 9. All right. Okay, so let's put 25 minutes on the Pomodoro timer and we will get started. So for this, let's start simply. Let's actually just do the steps it tells us right here. We'll create a tape. We'll just decode this string onto the tape, and then we could just look at index k to return our answer. So let's see, we'll have a tape. It'll be an empty string to start with. And then for every character in our input string, first we'll check if this character is a digit. So if our character is in, now I'm just going to use a string here, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So if this character is a number, then we have to multiply our current tape by this many times. So let's see, I'll have a repeat count. Now I need to convert this character to an int, so I use int and I'll pass in the character. And then we just repeat this tape that many times. So our tape will equal tape times this repeat count. And we'll just continue. If it's not in 0 through 9, then this is just a regular character, so we add it to the tape. So tape just plus equals this character. Now we have our tape. We've finished our decoding, and now we can just return our tape at, let's see, it's 1 indexed, so we have to do k minus 1. All right, and that's pretty much it. Let's see if this works. Lowercase c. Whoa, memory limit exceeded. Really, already? What are our inputs here? Oh, look at this one. I can see why our memory limits might be exceeded. Okay. Oh, interesting. So this index is just 1, even though this is really long. So maybe instead of going for every C in S, let's keep track of how long our tape is. So how about this? Well, the length of our tape is less than k, then we'll do this. All right. Now we'll need to keep track of our index. So C will be S at this index. So let's keep track of our index up here. Index will start at 0. And then we'll need to update our index every time we grab a character. So index plus equals 1. All right. So now for this, we're going to say while our tape is less than length k, in that case, we don't have the character yet. But as soon as we get to length k, we've got our character and we can return our value. All right, let's try that. Okay, so that works, and that actually works for this one case that we were running out of memory on. However, what if this k were some really large number? Building up this tape, we still might run out of memory. Well, let's give this a try, but I don't think it's going to work. I think we're going to run out of memory. Yep, and we run out of memory. Look at this input string though. Wow. All right, and our k, so it's no surprise we ran out of memory. All right, let's use this test case. Let's see if we can come up with a solution that doesn't actually build our entire tape. So one thought would be, well, let's go back to this. So this one would be a very long string, and it looks like we have some multiples of 9 in here. So one thought would be, let's build our tape up just until the point where it would be length of k, but we don't actually have to build it all the way to length of k. If we have some multiply, for example, let's say we have a string of length 10, and then it's multiplied by 9. That's going to give us a length 90 string or tape if we actually did the entire decoding. If our k is, say, 15, well, when we get to our multiply by 9, we don't actually have to create our string of length or our tape of length 90. We could just extrapolate, say, well, I have this tape of length 10. I know it's going to be 10 repeated a whole bunch of times. What if we just found what would be at index 15? And that might actually help us reduce our memory footprint for this. So now instead of actually keeping our tape, or this length tape, we'll actually have to keep a separate value for the length of the tape, the computed length of the tape. So let's see, this will be a tape length. We'll start that at 0. And then while our tape length is less than k. All right, now in here, when we increase our tape, we'll increase our tape length by 1. But then here, we'll increase our tape by this repeat count. So our tape length will equal tape length times the repeat count. All right. I don't know how that happened. All right. And instead of actually doing this whole thing, we don't actually have to do this multiply. So let's not actually do the tape creation at this point. This is where we might run out of memory. So let's just hold on to this. And we only do the tape creation if this is still less than k. All right, so now we're only doing our tape multiplication if our tape length is less than k. Now, once we've exceeded k, we don't actually have to do this multiplication. We don't actually have to extend our tape out this far. We need to backtrack, though, to figure out, well, where in this tape would our index lie? Oh, man, I think this is getting too confusing. Well, I'll just proceed really quick and try to get this done, but this is probably not the right way to do this. So we've basically figured out how long our tape would be, even though we haven't actually generated the entire tape. So somewhere between our actual tape length, or the length of our current tape, and the length of our calculated tape length, if we did the multiply, somewhere between those two lies our k value. So what we want to do is backtrack from our calculated length. We'll basically subtract our actual length. How many copies of our tape do we have to go back before we have our k within the range from our tape start to our tape end? So I'll call it like tape start index. And let's see, that's going to be tape length. And then while our tape start index is greater than k, we're going to be backtracking. So our tape start index minus equals the length of our actual tape here. All right, so I'm taking the length of our tape, so our calculated size or our calculated tape length. I'm going to be backtracking a certain copy, a certain number of copies of our current tape, just so I can find where in our range of our actual tape this k index will lie. All right. And now we need to calculate the offset from the start of our tape to our actual k. I am not describing this well at all. I am so sorry. I'm sure you're not following any of this. Here we go. So k offset. Well, let's see. That's going to be our actual k minus the tape start index. So basically, we have our k lies in the range from the tape start index to the tape start index plus the length of this tape. So basically, you can think of this as the one copy of the tape that has our k index in it. And since this is one indexed, I actually have to start at k minus 1 minus the tape start index. So this will tell me the index, the zero-based index of my k in my tape. So then I just return my tape at this k, or k offset. And my paste isn't working. All right. Okay, try this. So many typos. Okay, and that seems to work. Now we'll run this, but again, I don't think this is probably the best way to do it. Memory limit exceeded, but we actually beat 45 out of 45 test cases. Interesting. So it works, but we run out of memory. So again, even though we're not creating the entire tape, we're creating enough of the tape to make this run out of memory. Okay, so let's start the whole thing over, and we'll do this a completely different way. All right, so this is the better solution. This is not something that I came up with. So this is not something that I can describe very well, and this is probably not something I would come up with during an interview. But if you study this one, this might be the way to learn how to do this type of problem. So if you do see it again, you'll think back and say, oh yeah, I've seen this before. Maybe I can do this one. So we're going to do something very similar to what we just did. We'll calculate the theoretical entire length of our tape. So we'll do this here. Tape length, start it at 0, and then for every character in our string. All right. In this case, our C, if our C is, let's say if it's not in our numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So if our character is not a number, in that case, our tape length just increases by 1. And we can continue. Otherwise, this is a number, so let's get our repeat count. That's going to be the integer version of this character. And so our tape length will now become our tape length times that repeat count. All right, so now we've calculated the length of our tape. Now this is the theoretical entire length of our tape. If we decode this string, this is how long our tape will be. Now we'll start rolling back from this point. Let's go backward to try to find where our k index is. Okay, so to do this, we'll actually be working backwards in our string. So for every index in our string, and it's going to be in a range from the length of our string minus 1, so we'll start at the end index, and then we'll be going backward. So we'll be going to -1. So in a range, this is not inclusive, so we're basically going to 0, and the last step to -1 doesn't actually happen. And we'll be taking steps of -1. So this is working backwards in our string. We're going from the right side of our string to the left side of our string. All right, we still need to get the character at this index, so the character for this index. Now, if this character is a number, so if the character is in 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, So if this character is a number, well then we can reduce our tape length by dividing it by this number. So essentially, if we had a number, that means we basically multiplied the length of our tape by this value. So to find out how long our tape would be before we multiplied by this value, we'll just do a divide. So our tape length is going to equal our tape length, integer divide by, again, we'll have a repeat count. So I need to get the integer version of this number. So repeat count is equal to the int of this character. All right, and so we're working our way backwards. We basically created this long tape, and now we're going through and we're kind of rolling it back. Now that we've rolled back this tape by some factor, some repeat count, now if our k happens to be in that range, sort of the range between where this is now and where it was after the repeat count, so if our k lies somewhere in that range, that means our k is in our current tape. Let's call this a tape segment. So if this tape segment exists, previously this tape segment was multiplied by this number of times. It was repeated this number of times. Now that means that our k must be somewhere in this tape segment, before it was repeated. Or I should say, because this is being repeated, this is the only segment that we have. It's being repeated a certain number of times. That means it must contain the value that we're looking for. Let's see if there's a good way to describe it. Okay, let's see if I can draw a little picture here. So this is our tape segment. And I think my copy and paste is not working right now. Yep, not working. Great. So this is our tape segment. And we're going to repeat this, let's say 3 times. So we'll do this. All right. So let's say our k is here. Now if our k is here, now we know that this is our segment, and we're going to repeat it 3 times. This k is in one of our 3 segments. So that means that there's a mapping somewhere between the k in the entire range of all 3 segments and the k equivalent in just one of these segments. Now essentially that is going to be our k modulo our segment length, this new tape length. So let's see if I can do this here. I'll have a new variable here. We'll call this adjusted k. And to start with, we're just going to make it k. But now when we've divided our tape here into segments, this adjusted k will become the previous adjusted k. In this case, it's going to start at k, and we'll take a modulo by the tape length, or this segment length. So essentially that's just saying, what is the remainder if we divide this k position by this tape segment? So in this case, we would have 1 and it looks like a half. So 1.5 segments go into our k. Since it's a modulo, we drop the 1, it's just the remainder, so we just get this half. So we know that that is the index in our tape segment. All right. So that tells us our new adjusted k. Now what if this character is not a digit? If this character is not a digit, that means this is a character. This is potentially our answer. So let's do the easy part of this first. If this character is not a digit, that means that we can just remove this character from our tape. So our tape length will just be reduced by 1. That's the easy part. The more complex part is what happens with our answer. So we know our answer can't be in this segment, in this if part, because it's not going to be a number. It's not going to be a character. So that means this character is potentially our answer. How do we know if this is our answer? Well, this is our answer if this adjusted k index maps to this place in the tape, this character's location in the tape. And so we can check to see here if our adjusted k is equal to our current tape length. So again, this character is being removed from the end of our tape. That means this character is at this tape length index right now. So if the adjusted index that we're looking for, the adjusted K, is the tape length, we know that our current character is at this tape length index because we're removing it right now from that position in our tape. Then that means that this character is the answer. So we could say return C. All right, we have 1 minute left. Let's run this, see how we do. Okay, we're failing one case. Looks like we're not returning an answer. So let's see, if we don't find an answer in here, tell you what, it must mean that we have no character, so we just return s at index 0. Yeah, I think it means that we've gone through our entire range here and we didn't find the answer based on this, so we'll return string index 0. I don't know, I'm skeptical that this is going to work. Yeah. All right, let's jump back here. I think the key to this is right here. So if we've adjusted our K, it is the same as our tape length, or if it's 0. All right, so that works. Let's submit this, see how we do. And it passes. And we do okay. 80% for runtime, 65% for memory. Not too bad. All right, that's it for me. Hope you enjoyed this, hope you had fun, hope you learned something, hope you can go out and write better code.